Welcome to today's GATE session. Myself, Adly Melba Reena. I am Assistant Professor, Department of Artificial Intelligence and Data Science, S.A.E. Engineering College. So today's topic in our GATE session is machine learning. In machine learning, we are going to talk about support vector machine. We'll see what is machine learning. So machine learning is a subset of artificial intelligence where we are going to design a system which allow us to learn and make prediction based upon the experiences that we get from the data. So when we talk about machine learning, it can be learned by three different techniques: supervised learning, unsupervised learning, and reinforcement learning. So first we'll see the supervised learning, as support vector machine falls in this category. So supervised learning is a technique where we learn the data from the past input data, and that helps in the prediction of the data. So the supervised learning can be divided into two categories: classification and regression. And here in supervised learning we have many techniques, out of which certain support only classification and certain support only regression. But support vector machine support both the classification as well as regression. So what is special with support vector machine? So in order we are going into a supermarket to find out what the fruit is. We have two red color fruits there, and we just want to identify what the fruit is, whether it is apple or strawberry. So here we have many subsets here. So the best part with support vector machine is it looks into the data, sorts the data, and find out what are the different categories present there, and it sorts them into those categories. So in our case, what we said is whether the input data is an apple or an strawberry, the support vector machine first label the sample data. It will just go and check with the sample data, and it takes the labels out of which, and then it forms a decision boundary of it and see whether the similar data of shape or color and other features are being grouped together, and the other features which are being grouped similar are being grouped together, and a line is being drawn, and that is called as the decision boundary. And then we are just plotting the new data which we have, where we want to predict whether the data is that fruit is an apple or a strawberry. That is being inserted into the plotting area to see where does that fruit lies upon. And once it is being placed, we are able to predict the unknown data, and from that we are able to come to a conclusion that the unknown data is either strawberry or apple based on the position of the unknown data placed in the plot. So because of this discrimination given by the SVM, it is a best technique, like one of the best technique to predict the data. So we'll just see what is a support vector machine. So support vector machine is nothing but finding an optimal boundary to classify the objects. So first here we are just taking the data input, and then we are transforming the data, and then finding out the boundary with the help of a hyperplane, and then a margin is being maximized or minimized based upon the optimal value that we get, and then we classify and find out the data. So support vector machine is a discriminative classifier which helps us to train the data under the supervised manner, and it gives us an optimal result by categorizing the new examples with the help of a hyperlink. So the problem here, we can see a plot here. We have some black dots and blue squares in this one, and what is the problem is in this plot is we have to classify where the black dots are and where are the blue squares are. So how can we classify it? This classification can be done with the help of plane, or we can say a boundary that can be fixed, like drawing the line between it. A single line clearly distinguishes the type of the data. We'll see another example. See, this one tells us the need of the non-linear data, so how it has to be separable. So if the data are linear, as we said before, we can draw a clear line to it, and that can be separate two data into it. In this case, you can see here the data are non-linear, and this datas are similar and the other datas are similar. So you can see here this datas are similar and the other datas are similar. So in this part we cannot draw a straight line to clearly partition this is the similar data and that is another group of data. So this type of data is called as the non-linearly separable data. But when we talk about this particular data, you have a pink dots as well as the green dots. So in this case we can just draw a straight line to separate these two dots to say that these two are different datas. So we'll see another different type of non-separable data and see the different ways how we can draw a plane, straight plane to distinguish the data between them. So here you can see in this particular figure you have red dots as well as blue squares there. And the problem here is to classify the red dots and blue dots. But when we see here, this is an irregular figure where you have to draw either a oval or a circle to differentiate these things, which is not possible to linearly separable these data. So in order to overcome this, what we do is we change the plane of this, the plane. Now it is in XY plane. We are just introducing this 2D plane to a 3D plane and transform in such a way that we will be able to introduce a plane to it. So that same figure is being transformed. The XY axis, first we saw it in an XY axis and now we just transform the image in such a way that it is shown in XZ axis. So now we are able to see a clear distinction between the data. So the top layer is the blue star and the lower bottom is the red dots. So now we can just introduce a hyperplane, a plane. It is not a single line, it is a plane that is clearly distinguished between the top layer and the bottom layer. So here we say this is a hyperplane which is used to separate the data, and this 2D plane is drawn parallel to the x-axis so that it acts as a separator. So the next type of non-linear data is, you can see here you have the data and few of the data are slightly closer to the other data. In such a way, if we are going to draw a hyperplane for this, two of the black dots lie in the blue square parts, which says that there is an overlap in data. So this hyperplane misses some information there, so this can lead to a classification. So this doesn't give us the optimal result. How can the plane can be done for this is, you have to draw a separator in such a way that no black dot should fall in the blue squares and no blue squares should fall in the black dots. So this type of separator gives us the best result of classification, but this is quite difficult. It is a complex task and this can be achieved with the help of a regularization parameters. So what is a classification problem? So you can see a datas that are being present here. You have two types of datas, blue dots as well as the orange dots, and we have to create a clear distinction between these two dots, but it is not possible here. Whatever line we do it or whatever groups we do, we try to classify, we are not able to get the clear picture. So which line can be the best? So best fit is the problem here. So the SVM's main idea is not just to find separating line, but it should be the best one. The best line is the one that has the largest margin or buffer zone between the two lines. So finding the widest possible street that separates two neighborhoods with the street edges touching the closest houses. So the same data which we saw before is being transformed and it is tilted to the 3D image, and we can see here more number of green dots are present in the left hand side and the more number of red dots are present in the right side. So we can see the last data that ends there. Averagely we say that is the support vector here, and here the support vector which has the last one is being taken as the support vector here, and the total one is taken as the boundary. So this gives us the whole a big boundary here, so that we'll be able to classify the data correctly. So what is the concept of SVM is, we'll have a hyperplane, we have a margin, and we have the support vectors. These are the key concept of it. So hyperplane is nothing but the plane which clearly distinguishes between the data and gives us classify them into two parts. Either it can be a 2D. If it is a 2D, it is a line. If it is a 3D, then it is a plane. So in higher dimensions of data or the complex data, this will be called as a hyperplane. So the margin. So margin is between the hyperplane and the closest point. So the closest point between the either cases. So this aims to maximize the margin. So what is a support vector? Support vector are the data points that lie close to the hyperplane. That lies close to the hyperplane. So and they also gives us the edge of the margin. So these are the critical elements of the data set. So support vectors, data points, margins and all. So if you move the support vector, the hyperplane will also move. If there is any movement in the support vector, the hyperplane also will move. And if you have any movement in other points, the hypervector will not move. That is the data points. So in order to achieve all these things, to get an optimal one, we are in need of tuning parameters. So some of the tuning parameters that are being present here are margin, gamma, regularization and kernel. So what is a margin? So margin is a perpendicular distance between the closest point. So here when we see here, these are the closest point. So this is the hyperplane and this is the data points. So this one is the margin between them. So the best optimized line, that is the hyperplane with maximum margin, is termed as the margin maximal hyperplane. The closest point where the margin distance is calculated are considered as the support vectors. Next is regularization. So this helps in optimizing the SVM classifier to avoid the misclassification of the data, and this is referred as the C parameters. So if the C parameter is large, the margin of the hyperplane is small. You can see here it is very small. If the C parameter is small, the margin of hyperplane is large. You can see the hyperplane is large in this case. So there can be a miscalculation if the C parameter is small. So C is large. If the C parameter is large, there is a chance of overfit. So some other data can fall on it. If C is small, there is a chance of underfit. Some data from this can fall into the other category. And next parameter is gamma. So this defines how far it influences the data. So there will be a calculation of a pulsable line. So pulsable line is nothing but the separation. We are seeing what is the distance between this line and the data, and how much it influences the other data. So low gamma is the point that calculates far from the pulsable line or considered for the calculation. So that is far away. So these are the low gamma points, and the high gamma points are the lines that are being considered very close to the pulsable line. Okay. So the next one is kernel, which is a very important part here. So this is a mathematical function which is used for transforming the data, and this uses some linear algebra to do it. So different types of SVM algorithms uses different types of kernel functions. So different types of SVM algorithm depends upon the complexity of the data and how the data is. So various kernels that are present are linear kernel, non-linear kernel, radial basis kernel, sigmoid kernel, polynomial kernel and exponential kernel. So example, how this mathematical formula is formed is k of x comma y is equal to dot product of f of x into f of y. So here k of x comma y is the kernel function and fx comma fy is the dot product of n dimensional. We will see this with an example. So x is equal to x1, x2, x3, y is equal to y1, y2, y3 and f of x will be x1, 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 x2, x1, x3 and the same way it goes with the other 2 points x2, x1, x2, 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 x3, then x3, x1, x3, x2 and x3, x3. Likewise, it will have the multiplication for the f of y also. So kernel of x comma y will be the dot matrix of like x and y to the power of 2. So we'll have the example, numerical example here. X is equal to 1, 2, 3, y is equal to 4, 5, 6 and now when we substitute to the above equation, f of x will be 1, 2, 3, 2, 4, 6, 3, 6, 9 and then f of y will be 16, 20, 24, 20, 25, 30, 24, 30, 36. So when we do a dot matrix of this, using this formula, we'll have it as 16 plus 40 plus 72 and goes on and we'll get the final result as 1024 and that is the kernel function. So the challenge here is nonlinear data. So as the nonlinear data, we cannot draw a straight line. So straight line doesn't often exist and the data in real world is always not clean. We are coming across with many noise data, then outliers, so that there will be unclean data in it and drawing a simple straight line to distinguish the data is not possible to it. Kernel one is the magic behind this and that is the power of the SVM. So the idea is if the data isn't separable and it is in the current dimension, you cannot separate into two different datas. We turn that dimension to a higher dimension so that the data becomes separable. So you can see the image here, the datas are being present in the single line. You can see the red dots and blue dots that are being overlapping and there is no chances of us to separate this data. But when you change this dimension, this 1D dimension to a 2D dimension by transforming by giving the transforming function y is equal to x square, you are able to see a curve here and the data also have a uniform fashion here. And if you increase the function, kernel function, there will be a clear separable space where we can draw a hyperplane to it. So this is not linearly separable in one dimension, but in two dimension by applying y is equal to x square, the x and y coordinates are being separated in such a way that we are able to have a straight line. So what are the different kernel functions that are being present? For different problems, there are different kernel functions that are being present that gives us a different shape of decision making. So linear kernels are always for linearly separable data and we use a straight line to distinguish them. Polynomial kernels are nothing but a curved or a complex boundary which goes well with the complex data, and RBF kernel, which is nothing but the radial basis function kernel, which uses the Gaussian type. It is extremely popular and powerful because it can create a boundary for many complex circular or blob like boundaries, so that it has become as the default kernel options. Sigmoid kernel helps us to separate the classes process better if there are values above and below a threshold. If you have a threshold and the data are being distributed above and below, then we can go in for a sigmoidal kernels. So handling this type of meshy data can be done only with a soft margin. Hard margin is nothing but the straight line which gives a perfect separation of fail and non-fail data. So if you have a messy data there and if you implement a hard margin there may be a possibility of fail and overfit of it. So solution to this particular problem is soft margin SVM. So this has been controlled with the help of a hyperparameter C, and this is nothing but the cost or the regularization parameter. So if the parameter C is low, the margin will be wider and it will be more tolerant for miscalculation. So this is generally an underfit condition. If the hyperparameter is high, the margin will be very low and there will be a low tolerance for misclassification. So what are the pros and cons of SVM and where it can be used? So SVM is effective in higher dimension spaces. Even the dimension or the samples are high. Memory is more efficient and it is also uses only subset of data as support vectors. Very versatile due to different kernel functions. Works well on data sets with clear margins of separation. So what are the drawbacks are? Computationally it is very expensive and it is very for large data set it's even more higher. So it is O of n power cube or O of n square. So it is not great for noisy data set. It can be a black box, so that it is very hard to interpret the final model unlike the decision tree. So choosing a right kernel and C parameter is very tricky. That requires tuning. So where are we using this applications? In real world it has been used in many areas like image classification for the face detection, image recognition, then text and document categorization to identify the spam and filter the news articles, bioinformatics to classify the proteins and the cancer diagnosis with the help of gene expression data, and handwriting recognition as well as the outlier detection. So as we have seen, SVM is a powerful classification algorithm and it helps us to find the optimal hyperlink and it gives us the support vectors as the critical data points, and that gives us defines the hyperplane. The kernel allows to solve the complex and non-linear problem of for higher dimension, and soft margins make the SVM robust to real world noisy data and overlapping data and gives us a trade-off between the margins. So let's discuss some of the gate questions that has been discussed in SVM. So here is the first question. Consider the data set with 6 data points x1, y1, x2, y2 and it goes up to x6, y6, where x1 is 1, 0, x2 is 0, 1, x3 is 0, minus 1, x4 is minus 1, 0, x5 is 2, 2, x6 is minus 2, minus 2, and the labels are given by y1, y2, y5 is equal to 1 and y3, y4, y6 is equal to minus 1. A hard margin linear support vector machine is trained on the above data set. So which one of the following set is possible sets of support vector? We have to find out which is the support vector. So when we plot these points in the graph, we'll be able to see the particular image. You can see x1 lies in this x-axis, x2 in the y-axis, x3 also in the y-axis, x4 in the x-axis, x5 and x's are part away of it. So this clearly forms a margin and gives us a hyper plane to it and says that x1, x2, x3 and x4 are the support vectors, and this is the solution to it. So this can either be done manually or you can also use by the definition that we have already seen. We have to maximize the margin and find out what are the data points that pushes the to find the decision boundary. So the hard margin SVM is always linearly separable, or else we have to use a soft margin SVM. So based on that, we are able to clearly distinguish it. So the second question, the kernel function has been defined as r square into r square is equal to r is a kernel, and that has been defined as k of xy is equal to 1 plus x power t into y the whole square. So this is the function which they have been defined, and we have to find out what is the transformation corresponding to this kernel such that k of x comma y is equal to phi of x per t phi of y. So what is the idea? We have to find out what is this d. So this is the basic idea what we are going to do. We have to expand the kernel's output and separate the terms into those that belong to x and those that belong to y. Let's see the solution. So the answer is 6. So how do we get this? We are expanding the action of the kernel of x and y, and k of x comma y is being given with the expanded form, and we are just expanding the equation which is being given there, and that gives us as phi of x power t, phi of y power t. So here phi of x is nothing but 1 x square x1 square x2 square root 2 of x1 x2 root 2 of x1 root 2 of x2. So when we compute this, we are able to get the determinant which is 6. So the next question, you train a linear soft margin SVM on a data set with two features x1 and x2. If the data set is linearly separable, which of the following is true about the margin? The margin decreases as the regularization parameter C increases. The margin is independent of the regularization parameter C. The margin increases as the regularization parameter C decreases. The margin decreases as the data points are moved further from the decision boundary. So as we have already discussed, the first two is false, it doesn't hold good, and the last one is also doesn't hold good. The answer is the margin increases as the regularization parameter C decreases. So that is the answer. So why do we say this? As C decreases, the margin becomes wider, that allowing the hinge loss to keep growing. So that is the correct answer. I hope this has given a good idea about the support vectors and the support vector mission. Thank you for all, and let's see in the next section.